Dynamos of dance and bringers of funk, it's Prof G, and in this lesson we're going to learn how to create and code subscribers that respond to messages published when we press the disco button we built in the last lesson. We'll specifically learn how to turn on a strand of LED lights and run an animation, play songs from a micro SD card, and how to turn a projector on or off by toggling a relay switch. Let that funky big learning commence. Now here are the components that I've used for one of the subscribers that I'm showing here. So this one will play WAV files from a speaker and run an animation on a strand of LED lights. So I've used another Raspberry Pi Pico W with headers soldered on. I got this string of 5 meters of NeoPixel compatible LED lights from AliExpress. You'll have to solder wires for power signal and ground, but I think that these lights are really nice. There are a lot of them with a great density, and you can easily string these around things like desks and windows. Now, since WAV files are large and the Pico doesn't have much storage, I've also added a micro SD card reader. It comes with headers, but you're going to have to solder those on, and you should use this with a class 10 micro SD card, no bigger than 32 gigabytes, which is a lot of storage. If your computer doesn't have an SD card reader, you're also going to need one to transfer files onto the card. Now, you can use any speaker with a standard 3.5 millimeter audio plug and its own power supply. This one's powered from a USB port. Now, to attach the speaker to the build, you can either use 2 alligator clips with pin ends, as I showed in earlier lessons, but for a sturdier build, you might want to use one of these 3.5 millimeter breadboard-friendly stereo jacks. Your speakers are probably stereo speakers with 2 bands on the plug, but if you've got a mono speaker, you'll only see 1 band on the plug, and if that's the case, make sure that you use a mono jack, not a stereo jack. Those are different, and you can't use a stereo jack with a mono plug or vice versa. And you'll also need standard supplies like a breadboard, wires, solder, and heat shrink. Now here's the wiring diagram for hooking up this hardware. My students have had a prior lesson where they learned to use micro SD cards with the Pico, so if you haven't gone through that lesson, now would be a good time to check it out. Also in that lesson, my students created a library file called mount_sd.py, and it needs to be saved to your Pico's lib folder so that it can be used in our code. Be sure that you've created this and add it to your lib folder. I've also included a copy in our GitHub repo for this project. Here's a refresher on wiring up the micro SD card reader that I'm using. This is the SPI type. Now, this doesn't look like the NeoPixel strand that I'm using, but the wiring scheme is the same. 3 wires, power, signal, and ground. And if you're using the stereo plug, it will fit on the half-sized breadboard, but I've extended the diagram here so that it's easier to see the wires. Either of the outer wire provides sound, but if you have 2 speakers running from a single jack, you can run a wire between the 2 outer prongs to connect them. Then you can connect just one of the signal wires to your Pico. I'm using GP15 in this build, and the middle prong in these stereo jacks is ground. Now this build assumes that you have a formatted SD card and that card has a folder in it called disco_sounds_wave, WAV, all lowercase. Now if you change the name of this folder on your SD card, you're going to need to change the path variable in your code. Now I'm using WAV files in this build because I'm using the audio mixer library, and that can eliminate the popping sound that otherwise occurs when you play audio files back in CircuitPython. Now CircuitPython does play MP3 files as well, and MP3 files can be much smaller than WAV files because they're compressed. But if you use the MP3 code that we learned about in prior lessons, you'll notice a pop before each file is played. Audio mixer with WAV files will get rid of that pop. Now my Disco Songs WAV folder has 4 disco tunes that I referred to in my publisher code for the button, but there's a 5th file in here, disco_stew.wav. I play this sound after the subscriber is properly connected to the internet. If I hear the voice of the incomparable Disco Stew from The Simpsons,
Disco Stew likes disco music,
then I know everything should be working properly. Otherwise, I can unplug and plug my build back in, and hopefully things will start to work. And I've got a copy of that Disco Stew sound clip, for educational purposes only, of course, in the GitHub repo for this project. Now, WAV files used with CircuitPython should be formatted at a sample rate no higher than 22,050 Hz, but I found that the iTunes files that I converted to waves for some reason produced crackling in random locations when the files were played, and I even noticed crackling when the audio mixer was set up, but when I wasn't playing files. I spent a lot of time trying to figure out what was going on, and I discovered that if I set the sample rate of my files down to 16,000, that fixed the problem, at least for me. So the code I'm going to be showing you assumes that you've saved your WAV files at 16,000 Hz sample rate. Now, if you do change the sample rate from 16,000 Hz, do know that the Disco Stew WAV file has a 16,000 Hz sample rate, so you'll want to convert that to any new sample rate that you're using. Now, WAV files should also be saved as 16-bit, which is the default for WAV exporting in the free Audacity program that I use in my lessons. Now, CircuitPython does provide stereo playback, but I also found that sometimes stereo files produced constant clicking, and converting files from stereo down to a mono track fixed this problem. Now, I've got a whole lesson that describes how to format sound files this way using the free Audacity program, but here's a refresher on where you can find and change the sample rate, and where you can find the setting to mix tracks from stereo to mono. So at this point, you should have a properly configured second Raspberry Pi Pico W configured with CircuitPython and the appropriate modules in the LIB folder, and it should be plugged into your computer and show up as CircuitPy. The Pico should be wired as expected with a micro SD card reader and an SD card with a Disco Sounds WAV folder containing the properly formatted WAV files that you're using in your build, plus the Disco Stew WAV should be on that SD card and inserted in the SD card reader. Now, if you've got all of this set up, let's head over to GitHub. We're back in our Disco Button repo. This time, find and click on Disco Subscriber Audio Mixer Code. Click the copy icon in the upper right. This is the one that looks like two rectangles, one on top of the other. Then head back to Mu, click New, and paste this into the new tab. Then to save as, you can double-click on the Untitled tab, navigate to the CircuitPy volume, and save this as code.py. Then you can open your serial console and click Save, and if everything works properly, you'll see that you connect to the internet and to Adafruit IO.
Disco Stew likes disco music.
You should hear Disco Stew come from your speaker, assuming that your speaker is plugged in and turned on. But if you have any errors in here, like your SD card isn't being recognized, then you probably have a wiring problem or a soldering problem. You'll need those problems fixed before you can continue. Now, if you've been following the previous tutorials, you'll notice that much of this code works just like the code in our tutorial to remotely control a Pico W from a browser, but the difference is in this build, instead of using a web browser as our publisher, we're using our Disco button. So the imports that we've used are like the ones in the earlier lesson, but we're also importing mount_SD. That's the file you created to work with an SD card, and Audio Mixer, since that's how we're playing files here. Now, we're also going to use two animations, Solid and Rainbow, so I import those here, and we use the color wheel from Rainbow IO in the roll lights function below, so I import that. Now, my strip has 350 lights. I'm really pushing the limits of how much power VBus on the Pico W will supply for our rainbow animation. I could use a separate power supply, but I know that I'm probably going to use fewer than 350 lights in this build when I finally wrap them around my desk and my window. I'll count them up and change this after I string my lights. Now, my NeoPixels are connected to pin GP16. I'll also create the color black, and I'll turn off the lights in the strip I just created. And I'll assume the current animation at startup is solid. I'll set up the solid animation in black that turns off the lights. The variable current_animation holds the current animation, solid or rainbow. I'll set up the audio on GP15. The path is /SD/disco_songs_wave, WAV. SD is what the Pico uses to refer to your SD card. So even if that volume has a different name, your Pico still wants you to use SD in here to refer to the SD card. Then we set up the audio mixer. We only want to play one song at a time, so we'll set the number of voices to 1. Here is where we set up the mixer object. It's important to remember that the sample rate value here should be the sample rate that you use for all of your WAV files that you probably set up in Audacity. Now, I use 16,000 here. If you use a different value, change it here, but make sure that you update the Disco Stew file with that new sample rate, otherwise it won't work. So all of your files need to have the same sample rate. Then we play the mixer. There are no voices in here, but this is just used to set things up so they can start playing WAV files. Now, this play_voices function here plays a sound on Audio Mixer starting from the very beginning. The file name is passed in as a string. It should be identical to the file name on your SD card in your Disco Songs WAV folder. We only play one file at a time, so again, that's going to be the voice indexed at 0. But if there is a sound playing in that voice, we need to stop it before we continue to play a new sound. Now, I always like to print out the path and file name before I play a file, which can help when debugging if a file isn't found. Now, sometimes when playing a file in Audio Mixer, an error can occur, so I put code in here to read and play the file in Audio Mixer inside of a try block. I try to read the file I want to play, start playing at voice 0, the only voice I'm going to use. I set the level to 1.0, which is full volume, and if this doesn't work, I print out an error. You should be able to press the Disco button on and off again, and hopefully next time it'll play a song. Now, I did notice one particularly nasty error that occurred when I was testing this. It rarely showed up, but it was an error number 5, input-output error. Hopefully the code that I wrote here will catch that error, and instead of crashing or hanging the microcontroller, it will reboot the microcontroller from start so that the whole build doesn't crash. But if for some reason that doesn't work, I'll update the GitHub repo with a better alternative if I find one. Next is the roll lights function, similar to the function that I use in my disco button, but to have this run at about the same speed as the roll lights in the disco function, I provide a calculation in here to light up blocks of lights at a time rather than one light at a time. That's important because I'm using so many more LEDs here. You can tinker with these values if you want more or fewer lights to light up when you roll your lights. Now this next function here receives the current animation we pass in. We'll eventually get this from a message sent from the disco button. Again, at this point, I'm only sending solid and rainbow. And actually, I only call this when I'm running the rainbow animation, not when I'm running the solid, because I don't need to continue to update the solid. You do need to continue to update the rainbow. The fact that this is broken out in a separate function just will allow you to add additional code if you want to play around with different animations. And if the animation is rainbow, I run my rainbow animation, catching any error that might occur. The rest of the code is standard and it was covered in an earlier video. So this is where we set up our feeds, our connected and disconnected functions. The message function gets the message. If the message was a disco song name, then we play that voice in the name appending .wave at the end. Otherwise, the topic should be an animation, and if it is, I set the current animation to the message. If it's solid, I stop playing any sound that might be playing and I perform a single solid animation. This should turn off the lights, and I won't need to perform the solid animation again until the next time the disco press button tells me to turn off all the lights by sending the message solid. But if I receive the message rainbow, I roll the lights so that they go on in groups rather than abruptly turn on. It's just a nice effect that I've added. And then I try to animate with the rainbow animation. Here I try to connect to Wi-Fi. If it doesn't work, I reset the board, and that code should continue to run again from the beginning so I can try again. Then I set up my broker, connect, disconnect, and message functions. I connect to the MQTT broker. I play Disco Stew. If I don't hear Disco Stew, then I know something was wrong. But if I'm playing Disco Stew, I wait until he's done playing before I move on. Then in the while true loop, you don't need to repeatedly perform the solid animation if the lights are off, but if it's not solid, I perform the animation. Right now it's only rainbow. This just ensures that the rainbow animation continues to run with each iteration of the loop, so the rainbow continues to move and change. And in this loop call down here, this just makes sure that any new messages that come from the disco button are received and responded to. If there's an error that occurs, it's almost certainly that I've lost connection, so I try to reconnect here, and that's it. Now you can see I've got two builds here. My disco button is run on a separate Pico, not the code running in Mu. This build on the left is running my subscriber code in Mu. It's connected to a strand of 350 NeoPixels. It's got an SD card with my disco sounds wave files in that folder, and a speaker is plugged into the stereo jack on the breadboard. So with the serial console open, I'll save again. I'll hear Disco Stew. The display on the button says I'm going to play that funky music. When I press the button, you'll notice that I see the lights roll on my button build, but also you'll see the lights roll with blocks of lights progressively turning on in the NeoPixel strip attached to the subscriber. And there it is. Nice! Also, when I press the button, I can see messages printing to the console, just letting me know that everything's working fine. I can turn this off. Lights and sound both go off. I can select a new song, Boogie Wonderland. The funk is brought. Off. Change to Disco Inferno. On. Off. How about a little Bee Gees? The build is staying alive. Nicely done. Now to show you how you can make additional modifications to this code, here's how I added to this build so that I have a disco projector light go on when I press the disco button. Now here I have yet another Raspberry Pi Pico W set up with its own subscriber code. I'll show you the code in a moment, and this Pico W is attached to a relay switch. Now a relay switch can be used to toggle a connection and electrical wiring on or off. Relay switches can be connected to more powerful power sources. Now if you're new to this, definitely read up on how relay switches work and understand the power you're connecting to and any risks that you're taking. I am not responsible for any errors or any problems that happen. You're on your own to learn more about relay switches before working with this in your own builds. Adafruit has videos and learn guides. You can ask an electrician or an electrical engineering friend for advice, but be sure you understand any risks that you're taking. That said, let me show you what I did. One uses relay switches because the power coming from the wall outlet is going to be too much for the Pico, so a relay switch can toggle power on or off programmatically without any power traveling through your board. Now here's the relay switch that I'm using. I bought it off of Adafruit. Now if you want to connect this to a breadboard like I've done here, you're also going to need a stemma cable, not stemma QT. This cable should have 3 wires with pins at the end. Those 3 wires are power, signal, and ground. They head to the Pico. Power can use any power pin, ground any ground, and I happen to be using pin GP17 for the signal. Now to toggle power on or off, you'll use this side here with 3 holes. You only use 2 of them. My relay switch is connected via an extension cord. I've cut the power line, not the neutral side. You want to leave that untouched. You can usually tell the neutral side because the extension cord has ridges on the neutral side of the 2 wires inside of it. Also, the neutral side usually comes from the larger of the 2 prongs on the plug. I'm just using a simple 2-prong extension cord. So again, you don't want to use this for anything that's too powerful. Also very important when working with devices like this, make sure everything is unplugged when you're cutting, stripping, soldering, or wiring things up. If you don't do that, you will get hurt. That's not good, so unplug everything first. So with everything unplugged, I separated the neutral wire and the power side at one part on the cord. I cut the power wire and I stripped the ends of the cut wire, but then I discovered the wires in my power cord were braided. So the power or live wire is actually a bunch of smaller copper wires, not one thick wire. Braided wires are tougher to insert into the connections on the relay. They also don't hold very well inside these little latch holes, and you never want any of the individual wires in the braid to creep out and touch the other end of the wire. That would be bad. So I soldered a single core wire to the braided wire. I used heat shrink to make sure that no wires were exposed, and then I just pushed the solid core wire hard into the relay hole. You'll notice that it catches in here and it shouldn't push out. Always be careful when using relays. You don't want to put these out in the open. You want to make sure they're housed in a safe place so that the ends aren't pulled out of the relay switch. Now notice I've got one part of the live wire going into the middle COM or common, and the other side is going into NO for normally off or normally open. That's because I want the default to be off or no power going through the relay. Lady Ada suggests using these for 60-watt projects, so consider that a low-power light bulb. You don't want to use this for anything heavy-duty. You certainly don't want to run your washing machine off of this, but our little disco ball is fine. But when this works, when I press the button and send a message to turn on the rainbow animation, you should notice that the relay closes. You might even hear the little magnetic connection being made, and the disco projector will turn on. Then when I send the solid animation, the connection is broken, and the disco projector has no power running to it, so it turns off. Now let's take a look at the code for this. Now remember, at this point, you're probably going to work with yet another Pico W, so make sure that you've got that device properly configured with a settings.toml file for your network and Adafruit IO account, and it should be plugged into your computer. So you'll find a code for a subscriber using a relay switch in our disco button repo. You can find the file named disco subscriber relay switch.py and click to open that. Then click the copy icon in the upper right-hand corner, return to Mu, click New to open a new tab, paste in your code, double-click Untitled to bring up the Save As dialog box, then save this to your CircuitPy volume as code.py, and if you open your serial console, you should notice that you connect to your Wi-Fi network and Adafruit IO. Now let's take a look at this code. So the imports are even fewer than we had before, since we're not playing audio or working with NeoPixels, and the relay switch doesn't have its own library either. It does use digital IO, so make sure that we import that. But the setup is super easy. Relay switches are simply digital output devices. I've set up mine on GP17. Make sure you set the direction to output, and I initially set up the relay value to false, meaning no power is headed through the relay. So there's no connection between COM or common and NO, meaning we're normally off. Now, everything else in here is familiar to you. You've seen the setup of the username and key and feed variables. We're only subscribing to the animation feed in here. Now, the message function is different. We're going to respond to the animation message. If the message is solid, remember that means that the LED lights are off. So we should also set our relay.value to false, which opens the switch so no power flows from NO to COM and the disco projector turns off. But if the message is rainbow, we set the relay.value to true. This closes the connection so power flows through NO and COM. The disco ball gets its power and it turns on. Now everything else in the code should be familiar to you, connecting to Wi-Fi, setting up the broker and connecting to Adafruit IO. And down here in the while true loop, we always check client.loop to see if we have any new messages coming in. And if there's a problem with checking the loop, we just reestablish the Wi-Fi and Adafruit IO connections. And that, my friends, is it. So let's click Save, open up the serial console, connect to Wi-Fi and Adafruit IO. At this point, my extension cord is plugged into an outlet and my disco ball is plugged into the extension cord. Press that button and the rainbow animation is sent to both of our subscribers, and we see the disco projector is on, the relay's working. After it's pressed again, we send a solid animation, and that turns everything off. On, looking good. Off, looking great. Now that's it, Groove Coder. I hope that you now feel armed to create your own Internet of Things projects using MQTT, Adafruit IO, and CircuitPython. If you build something cool, post a video or pic to the socials with the hashtag BuiltWithProfG, and be sure to @ me so that I see it, and you might win the weekly Happy Gear laptop sticker. Be sure to like and subscribe. Now go and make something awesome.